All right. Once again, happy Tuesday. Welcome to section 3.2. I'm kind of excited about this because we need standard deviation for everything we do from here on out, except for chapter 4 and chapter 5. Chapters 4 and 5 are a little bit different. We kind of take a step away from our normal stuff and do some cool stuff with 4 and 5. And then we're going to use standard deviation for everything we do from here on out. And it is so useful and so interesting. Well, to me it is, but I'm also kind of a nerd. But it's pretty interesting. The empirical rule, it's really cool. And there's a little drawing you get to do that you're going to do 8,475 times this term. You're going to have it so ingrained in your brain. And I'll give you a couple little hints with it. And I'm going to give you a fun calculator function. So I hope you have your TI-84 calculator handy. It's going to be probably halfway through the lesson before we get there. This lesson will probably go fairly quickly, like on Tuesday. So just FYI. All right. So today we're going to talk about the range of data, which will take all of a minute and a half. It's one slide, a minute and a half, and we're done. Then we're going to talk about standard deviation and variance, and then the empirical rule. The empirical rule is something, it's one of those things that if you get it, you get it, and you're like, okay, I've got this and all of that. Some people really struggle with it, and I'm hoping I can help you overcome that. It's usually not a big obstacle, but I'm telling you, I recommend drawing diagrams, and I'll explain more later. I'm not even normally a draw a diagram kind of person when I do math, but I'm totally about draw a diagram when it comes to empirical rule. So let's get started. So the way we would determine range from raw data is as simple as take the largest data value, subtract the smallest data value. It's as simple as that. What is the largest minus the smallest? That's the range. There you go. There's your 2-cent explanation. That's what the range is. Largest data value minus smallest data value. And I don't know why I've never seen, except for this slide, I've never seen range with a big R equals. This slide is the only place I've ever seen that. So I don't know. Take that for what you will. So here for the travel times that we used on Tuesday, we take 43, which was our longest time, minus 5, which is our lowest. So there's a 38-minute range between the shortest travel time and the longest travel time. That's it. That's all there is to it. All right. Okay. Standard deviation. This is a big topic. Hope I don't confuse anybody. I know that that formula looks super scary. Thankfully, it's a little bit simpler than it looks. There's a lot of little steps, but it's a little bit simpler than it looks. So once again, for population, we have a fancy symbol. It's the Greek letter sigma. This is the lowercase sigma. So we use the lowercase sigma to denote population standard deviation. What standard deviation is, essentially it is the average distance all of the values are from the average, from the mean of the data. We only use standard deviation when we're using mean as our middle term, as our measure of middle. So standard deviation and mean are buddies. They go hand in hand. They work together. So if you're using median, you won't use standard deviation. And next week, I'll tell you what you're going to use instead. But so standard deviation works with mean, and it by averaging the distance, all of the values are from 0, it is giving us a measure of how spread out our data values are. So a larger standard deviation means there's a larger average distance from 0. So my data values are more spread out. A smaller standard deviation means there's a smaller average distance from 0. Therefore, they're compact and they're closer to the mean. They're not as spread out. So standard deviation just tells us how spread out the data is. So I'm going to tell you how to calculate it, and it's not going to make a whole lot of sense. and then I'm going to show you and hopefully it'll stick in your noggin. Okay. So you take each data value, subtract the mean from that data value, and then square it. And after you've taken each data value and subtracted the mean and squared it, then you add all of those squares together. After you add all those squares together, divide by the number of data values you have. Now that you're there, take the square root. That's the standard deviation. It's okay if that's confusing. I'm going to show you and it'll make a little bit more sense. We're going to work through this together. Does anybody still need this page? I can move on.
Will you repeat what you said? You said each data value, subtract the mean,
Yep.
add them all together.
Yeah, so we subtract the mean from each data value, then you square it. I have they're listed right here.
Oh, okay, I see.
Yeah.
Thank you.
Yes.
Was getting ahead of it.
Yeah, no, you're good. So you find the population mean. So I mean, I already mentioned the mean, but you're gonna subtract the mean from each data value, then you square the result. So you're gonna square that difference. Then you add all of those squared differences together and divide them by how many data values you have. Then you take the square root. We're going to do the math right here. Right here together. We're going to do it right here. First thing we need to do, does anybody still have handy what the mean was of the travel times? Or I can do it again, but I just didn't know if anybody had it handy. I can just put it on my little calculator right here. I wish I'd have just written it down and remembered it. That's not right. Okay.
She wrote it. She said 249, I think 24.9.
24.9. It is. Yes. Okay. So our mean, oh, yep. Sorry, I didn't look over there. So 24.9 is the mean. I really should just keep track of this stuff. Silly me. Okay. So what I'm going to do is I'm going to take each of these data values, I'm going to subtract the mean, and then I'm going to square it. So we have 23 minus 24.9 squared. So if you're doing this in your calculator, use parentheses just as I have written it. So you do parenthesis 23 minus 24.9, close your parenthesis, then hit the x squared button. We'll do the next one. Okay, thankfully we already have. Oh, what the heck am I doing? See, nobody told me I messed up. Second here. Okay. All right. One more time with feeling. It's been a really long week. There we go. There we go. 123. This one we have. I'm really thankful that this is not a large data set.
Yeah, like the homework, writing out every single, I was like, are you kidding right now?
Let me tell you, I'm going to show you a fancy way to use your calculator to calculate this. Whoa. So you don't have to do large numbers or a ton
Which
of.
I totally watched after I did all of it.
Oh my
And
goodness.
yeah, and I have a question about it later on once the class is ending, because the calculator gave me a different standard or a sample standard deviation, and I kept rechecking my math. I even did it on paper, and I had it right and the calculator had it off. So I don't know. I'll have to show you.
Quite possible. I mean, the biggest mistake is usually typos, but I don't know if you typoed in your calculator or not. Okay. We've done, and I took every single data value, I subtracted the mean from it, and then we squared that difference. So now I'm just going to add all these together. So now that's the next step. So we just did the step 2. Now we're going to add all of these together. Of course, I forgot my fancy calculator at school. So I have an emulator on my phone, and it's not as friendly as the nice ones as the actual calculator. Okay, so I have 902.87. If anybody's mathing along with me, make sure you correct me if I make a mistake. Please. All right. So now we take the sum. So that was the sum of all of them. And I need to divide by how many data values we have. So we have 7 data values. So I'm going to divide. So we have this equals, my eraser likes to just decide to turn on 128.98. That's ugly, but okay. Finally, we take the square root of our result. It's second x squared to take the square root on your calculator. So my standard deviation, here's my sigma, is approximately 11.36. So when you added them together, you got 875.87. Okay, let me try it again.
I got what you got.
You got what I got? Okay. Thank you.
On the tests, are we always going to round if it's 11.356? Are we always going to?
Yeah. You always round. If the next number is 5 or greater, you round. Yes.
Okay.
Yeah, so standard rounding rules apply here. All right. So this is the standard deviation. So this is what, I mean, we haven't learned the empirical rule yet, but we're going to be able to make be able to tell, like, if this wasn't a population, let's say if this was, especially if it's a sample, it would be super helpful to have an idea of where we would find most of our data. And that's kind of what this is doing also. So if I just told somebody, yeah, the average driving distance from to work is 24.9 minutes, it is minutes, with a standard deviation 11.36. This tells me a lot because now I can tell, I can use the standard deviation to determine about where most of the driving times are minutes wise. Standard deviation can tell us where the bulk of the data is going to lie. And that's what we're going to get to with the empirical rule. But right now, that's how you calculate it. We are going to do another one. I'm going to have you work through it. And I will work behind you. So you're going to do, all in all, we're going to do 1 more by hand here. And you're going to do 2 more by hand on the hand-in homework. And I will never, ever, ever ask you to do it by hand again. So you'll do a total of 4 times standard deviation by hand. And then after that, it's your choice if you do it by hand. You'll never have to do it by hand again. All right. So here's the test data. So what I would like you to do is I'm hoping you printed this out because this is a really nice workspace. But if you didn't, it's okay. Just use your paper. I would love it if you would calculate this by hand. If you don't, that's fine. So I will work quietly behind you. If you get stuck, feel free to look up and see what I'm doing, but go ahead and start calculating. Our mean here was 79. Oh, wait, I forgot we are going to do a sample standard deviation, but don't worry. Okay, our mean was 79. I remembered this one. What? I don't know what I just did. Here we go. I worked pretty fast, so I'm going to give you another minute to finish up. I just kind of got in a roll. How'd we do? Yeah. Okay. Any questions on how to calculate standard deviation? All right. Can I move on, or does anyone want me to hold on here for a second? Okay.
Quick question. Is it generally an approximately symbol?
Yeah, nobody's going to get mad at you if you don't do the squiggles. You're never going to it's never going to be exact. I mean, I don't want to, I guess I should never say never, but it's pretty rare. So 99% of the time it's going to be a rounded number. So I just like to put the squiggles. You don't have to. I'm not going to get mad at you. So, but yeah,
Thank you.
it's squiggles. They're more fun to draw than an equal sign. So if for no other
Is,
reason, go ahead.
sorry, is this standard deviation, is that like the scientific way of saying like plus or minus?
No, 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 no. This is just telling you how spread out the data is. It's and
So it's not saying it's like the average plus or minus this number.
no, no, it's just saying that because distance is always positive. Standard deviation is always going to be positive because I don't go -5 miles somewhere. Distance is always positive. Standard deviation is a distance. So it's always going to be positive. It's telling us the average distance each value is from 0. So, and this are from the mean, sorry. So for these test scores, on average, the test scores are 9.82% away from that 79% mean. So it's kind of telling us how spread out the data is. You're going to get a little bit more picture of what it is once we hit empirical rule in a few slides. So I'll give you a better picture. All right, I'm going to jump to the next page. We're going to talk about sample standard deviation. So once again, sample gets the short end of the stick. They don't get a fancy symbol. For sample standard deviation, we use a lowercase s. This one is calculated differently. And it is exactly the same, except we divide by n-1 instead of by n. So we divide by 1 less than the number in our data set rather than by the number in our data set. The reason we do this is because we know, remember when we were calculating means and every mean was different, was a different value. None of them were exactly what the population mean was. Because there's so much variation in the answers you can get when we use a sample, we have to account for that by making our standard deviation just slightly bigger. Saying we need to kind of take into consideration that we might have missed some extreme values when we took our sample. So our standard deviation is going to be just a little bit bigger to kind of account for that error. So we divide by 1 less than the number of our data set. It's called n-1 degrees of freedom, but don't even worry about that yet. We don't even have to worry about degrees of freedom until we hit chapter 9. So pocket the words degrees of freedom. I'll pull them out again, chapter 9. Just remember that you're dividing by 1 less than the number in your sample. So the only difference with the look of the formula is we're using X bar instead of mean. So this, because it's a sample, so we use the X bar instead of mean, and instead of a sigma, we're using an S. So we're going to do one sample, standard deviation by hand. Then I'm going to show you fancy calculator stuff. Okay, pop it onto the next screen. So here's our sample. We have a nice sample of 3. So I'm going to find the average of these 3 here. I'm going to find my X bar. 5 plus 26 is 36. I don't know why my cat's always crazy when I'm on Zoom. Okay, so my X bar is 22.3. So we're just going to get the sample standard deviation with these 3 values. I'm going to do 5 minus 22.3 squared. Uh-oh. $299.29. 26 minus 22.3 squared. $187.69. Once again, we're going to add these 3 things together. 500.67. So instead of dividing by 3, because that's our data size, that's how many data values we have, we're going to divide by 2. That's n minus 1. We're going to divide by 2. I got 250.34. Now, finally, we take the square root. So my sample standard deviation is approximately 15.82. Look, I didn't even squiggle. I don't know why I didn't put squiggles. So my sample standard deviation is about 15.82 here. So the only difference is we divide by 1 minus the population or the size of our sample rather than the whole sample size. Questions? Okay. Ready to use your fancy calculator? I'm going to use the test scores. So I want to pull those up. I'm going to use the test scores. Go over to my calculator. Okay. I will do this slowly. Make sure you stop me and ask questions if you need to. So the first thing we need to do is we need to enter our data into our calculator. So in order to do that, hit the STAT button, which is right here. Make sure I'll see my calculator. Okay. Hit the STAT button. And then we want the first option, which is edit. And it's going to bring all these lists up. You may or may not have stuff in your lists. I always have stuff in my lists. So you arrow up. So these little arrows right here, these are this round thing. The top one will arrow up. I don't know what I just did. Arrow all the way up. Oh, that's what happened. I went too far. What the heck? Okay. Come on. Okay. Arrow up until the L1 is highlighted. And then hit clear, enter. Do not hit delete. Hit clear, enter.
What did you hit after stat?
So stat, then edit. Edit is the first option. That gets here. So then you arrow up till L1 is highlighted and then hit clear, enter. If there's anything in your list. If there's nothing in your list, then you're golden. To enter numbers, just put the number in and then you hit enter. So the enter is down here at the bottom. So just put the number in and hit enter. So we're just going to do that for all 10 of our numbers. Give you a second if you're copying my numbers down. I highly recommend after you put all the numbers in there to stop and check them because my most common error is having a typo in my calculator. So I highly recommend just like looking back over the numbers, making sure you didn't type in anything funny. Hey, mine look good. All right. Now you're once again going to hit the stat button, which is right here. Hit the stat button and use the right arrow to arrow over to calc. You should have this screen. We want one var stats. This is one variable statistics. That's the screen we're going into. One variable statistics. And I'm going to hit enter and it'll bring the screen. So it should look like this. Okay. Our data is in list 1. If yours doesn't already say L1 there, then you're going to need to make it say L1. The way we do that is you do second L1. If you put your data in L2, you would do second L2. Whichever list you put your data in, it's just second and then that number. So if you look, I'm going to make this big. You see all the L1, L2, L3 has all the L's right there. So it's just second and then whichever one of these numbers it's in. Get smaller again. All right. Now just go down, leave frequency list, leave that blank, go down to calculate and hit enter. And you should have this lovely screen right here. Okay. So this first, your calculator is always going to call the mean X bar. It just assumes everything is a sample. So it's always going to call it an X bar. But regardless, this is your mean. That's the exact mean we had, so that's good. The second one is the sum of everything. So it is all of them added together are 790. This is the sum of all the squares. I've never needed the sum of all the squares, but it is so nice that it's there for us just in case we need it. This right here, SX, is your sample standard deviation. Sigma X is the population standard deviation. And wouldn't you know, that's the same number that we got when we did it. So the sigma X is population standard deviation. SX is sample standard deviation. Always remember that the population gets the fancy symbol. They always do. N is how many objects you have. And I'm not going to go through the rest of them. I'm going to go through the rest of them on Tuesday because they're not going to be meaningful until Tuesday. Actually, I mean, the median's right down here. I guess I could tell you that because we still do median. Median, if you arrow down a little bit, median is right down there. But I'm not going to talk about all the rest of them until Tuesday next week. That's when we're going to learn about those. Questions about one variable statistics?
Are the steps for the calculator written down somewhere?
No, you need to write them down yourself, or you can Google them, or yeah, I don't have them actually written down anywhere.
There's a video that she posted that was really helpful for me. I just copied exactly what it said, like the steps and then what everything means on there.
Yeah, and thank you. I'm sorry for interrupting you. Yeah, if you go down to, it's week 2 materials. If you go down here, descriptive statistics on the TI 8384, this one right here also walks you through it, this video. So if you need a walkthrough without finding the spot on this video, it walks you through it right here as well. Is that the video you were talking about?
Yes, and it is slightly different. When you hit stat and then you go to or your one variable calculation, his does not do the list frequency list calculate. So it's like one step different.
And it's like there's so many different, even with the TI 84, there's like I think 3 different versions of TI 84s. And then there's TI 83s. I mean there's several different types of graphing calculators. So one of the reasons I post that video is because I know that mine is sometimes a little bit fancier than some that other people have.
No, it was great. Yeah.
Okay, perfect. Yep, so that video is available for you. Also, if you want me to, I'm happy to type out the steps for you. If you send me a message and you're saying, I can't remember how to do it, I'll respond and I'll type out the steps for you also. Okay, let's go back. Where are we? There we are. Okay. We doing good so far? We hanging in there? So excited about the empirical rule. All right. I don't know that we needed this. I don't know why that's there. Okay. All right. So we're going to talk about this is a use for standard deviation. So comparing standard deviations. So we're going to take a look at McDonald's and Wendy's. So this is wait time at McDonald's and Wendy's. In my brain, it's the drive-through, but I don't know if it is or not. So we're going to take a look at the standard deviations of the wait times at both McDonald's and Wendy's, and we're going to compare them and talk about what it means. So these are wait times. Somebody ordered food, they got their food, I know that the fast food restaurants have like timers. And the reason I think it's drive-through is because it times it in the drive-through how long it is you are at the window. So standard deviation for Wendy's for this sample was 0.738 minutes to wait for your order. Sample standard deviation for McDonald's was 1.265 minutes. So McDonald's had a wider variation of wait times. So they were more spread out over a longer period of time. Therefore, their standard deviation is larger. Wendy's being smaller means that they have more consistent wait times. It doesn't even mean that they're better. It just means they're more consistent, which means they're more predictable. So I don't even, this does not give us any idea of who's faster or who's better, just who's more consistent, who has a smaller window between their largest and their smallest, a smaller average distance from the mean. So if you're looking for consistency, Wendy's is your best bet here. So that's what that means as far as standard deviations go. I think you have a question in your homework that says something about two different investment bank places, and one has a larger standard deviation than the other. Which one would you choose? The one with the smaller standard deviation is going to give you a more consistent rate of return, more predictable. Questions about that? Okay. All right. So variance is something I have never ever used in my entire life other than answering questions in my stats class that just say, what is the variance? I don't know any good use for variance, but here it is. All that variance is the standard deviation squared, or it's before you take the square root and you're calculating the standard deviation. So that's all variance is. It's the standard deviation squared. You will have some questions in your homework that ask you for it, but I've never applied it to anything. And I've never been asked to apply it to anything. But you will be asked what's the variance, and you will just square the standard deviation. And there you go. There's that exciting piece of information, and we're all better for knowing it. All right, moving on. Yay, empirical rule. Okay. This is a lot of data or a lot of words, and this is all important. The picture is going to be much better than the words, but the words are important. Once we get to the picture is your gold. Okay. Approximately 68% of your data is going to lie within one standard deviation of the mean. So if I add the standard deviation to the mean and find it and then subtract the standard deviation from the mean, in that interval, 68% of my data is going to be there. 95% of my data is going to be within two standard deviations of the mean. So add the standard deviation twice to the mean, then subtract the standard deviation twice from the mean. Within that interval, 95% of your data is going to lie there. So that's most of it. So this is the picture right here. You are going to draw this 8,742 times this period, this term. Not really, but you're going to draw it a lot. I hope you will. Super useful. So this is the empirical rule. So in here is 68% of my data. I forgot I wanted a highlighter. Go. So in here is 68% of my data is going to lie in here. 34% will be between the mean and one above the mean, one standard deviation above the mean. 34% will be between the mean and one standard deviation below. Then add another standard deviation out here. It's going to add 13.5% more on either end, so that's 95% total. I'm going to just not highlight this because it's ugly. Then add a little bit more. 99.7% of my data is going to be within 3 standard deviations of the mean. And then everything else is just outside of that.
This was where I had my question because I did a couple homework problems and it was because I added that 0.15% to the end of that. When do you use that? Is because
That's that 0.15% is outside of 3 standard deviations from the mean.
okay, because all of that together is 100%, right?
Yeah.
Because one side's 50, the other side.
Right.
So I don't. So what question would I like answer?
Okay. So if I said, okay, I'm gonna have a so let's say I'm just gonna put random values down here. So let's say that my mean is 50. Let's say my standard deviation is 2, just because this is easy math. So this would be 52, this would be 54, this would be 56, 48, 46, and 44. So let's pretend this is my data set, okay? I have a set of data that my standard deviation is 2, my mean is 50. I want to know, let's say that I want to know what percent of all data values are above 52. If I said what percent is above 52, that would include this right here, this right here, and this right here. That's when I would add all those together. If I wanted to know. So if I wanted to know what was above 52, I would add those three together, because all three of those would be above 52. I'd add all three of those percents. But if I wanted to know what percent is within 46 and 56, then I would add this one, this one, this one, this one, and this one. This is why I draw the picture. This is
No, yeah, that makes a lot more sense because I was trying to do the fill in like the guy was explaining in the video and I just didn't know what the 15% because I realized that 34 is for 1, 13.5 is for 2, but I just the yeah, it was just I don't know. Thank you.
You're welcome. Okay, so you can either draw this 500 times. Another thing you can do, if you have a dry erase marker and you have a sheet protector, print this out, put this in a sheet protector, and get your dry erase marker, and you can label it for these problems. And you can shade things and draw on it, and then erase it, and then use it for the next problem. I've had many students in the past do that, where they've just taken, printed this particular drawing and put it in a sheet protector, just used a dry erase marker on it. Or you can keep drawing it. I just whip one up really quick and just draw it really fast. But it's a great way to kind of remember what the percents are. Okay, so important thing, and I'm going to mention this a few times because it seems to be something that people struggle with. All of these are anything outside of this square right here that I'm going to draw right now. Anything outside of here, anything outside of here is considered an outlier. All of these are outliers. Anything out here, outliers. So anything more than 2 standard deviations from the mean is considered an outlier. You're not going to need that for your 3.2 homework, but I want you to file it away somewhere in your brain because you will need it soon. So somewhere I'm going to bring it up again. I'll bring it up 5 more times, or more than that probably. But this is your first introduction into outliers. Anything more than 2 standard deviations away from the mean is an outlier. There you go. Okay. I'm going to move on. Next page. All right, so we're going to use this now. And I already kind of did. I already kind of gave you a brief intro to that. So this data, it represents the serum HDL cholesterol of 54 female patients of a family doctor. So don't worry, you don't have to put this in your calculator or anything crazy like that. So I'm going to give you the population mean and the standard deviation, and we're going to draw the histogram. So the empirical rule only works if our data is bell-shaped. Only if it is bell-shaped, symmetric, So it's only going to work then. So here's my my mean is 57.4. My standard deviation is 11.7. This is roughly bell-shaped, and that's all we need. Roughly bell-shaped is good enough. I mean, it looks like it might be slightly skewed right, but it's close enough. So there's our mean and our standard deviation. So what we're going to do is we're going to figure out, well, we know this. According to the empirical rule, we know that 99.7% of all of our patients should have their cholesterol within 3 standard deviations of the mean. So let's take a look. So what I did is this is the mean right here, and I took the mean and I added standard deviation. So my standard deviation was what? 11.7. Oh, hold on. So I took 57.4 plus 11.7, and I got that right there. That's where that number came from. I added the standard deviation to the mean to get that first value. Then I'm going to add 11.7 again. That give me that value. And then add it again, and you got that value. So I just added the standard deviation to the mean, and then added another one and added another one. That's how I'm getting these values. That's how I'm labeling my curve. Then the opposite the other way. So this way, I subtract 11.7 to get this, subtract it again to get that, then subtract it again to get that. So I subtracted it from the mean 3 times. Okay. So what this is saying, what percentage of all patients have serum HDL between 34 and 69.1? So I add this percent, this percent, this percent, and that's it. So I add all of those percents on my curve between those two values. Uh-oh, I did something weird. So that's 47. That's not right. 68 plus 13.5. I apparently can't add. So 81.5% is how many patients have serum HDL between 34 and 69.1. I just added those percents together. See, drawing a picture, so helpful. It is draw and label. So what this wants to know is the actual percent. So we need to go back to our data and see the actual percent. So 34 and 69.1. Okay, let's take a look. Okay. I'm going to circle them. It probably would have been easier if I'd have crossed off the ones that weren't, but I'm going to do that right now. I'm going to read. That's going to be easier. Okay, I'm going to cross off the ones that are not between 34 and 69.1. Okay. I need to get rid of the 70s, rid of the 80s. See, I'm really bad at this. I'm bad at the numbers. Okay, those are good. Those are good. Those are good. All the rest are good, right? So I just have out of 54. So let me see. Uh-oh, done. Clear. So 45 divided by 54. So that's 83.3. That's pretty close. So in this sample, 83.3. So the The actual percent, yeah, I just counted that there were 34 or 45 out of 54 to get the percent, the actual percent. Now, the empirical rule is an estimate. I'm just letting you know. If you go to the tutoring center, they're going to show you a fancy calculator function to calculate the percents of these things, and they're not exactly the same as the empirical rule. Just letting you know this right now. Because the assignment for 3.2 wants you to use the empirical rule. So don't use the fancy calculator function if a tutor at the tutoring center helps you. Make sure you let them know that you need to use the empirical rule. Same thing with the hand-in homework. Number 6 on the hand-in homework, I'm expecting you to use the empirical rule. Don't use the fancy calculator functions. We'll use those later. The empirical rule is a kind of a rule of thumb. It is super close. It's close enough that nobody's going to get mad at you if it's slightly different. So just letting you know, the empirical rule is not exact. It is like a rule of thumb. So for 3.2 and for the hand and homework, use the empirical rule, please, please, please.
Same with the test. If it says, does it say to use it?
Yeah, I believe the question says, according to the empirical rule, what percent, yada, yada, yada.
Okay, thank you.
But if I specifically state empirical rule, I want you to use the empirical rule. Because the thing is, I know the fancy calculator function, but 99% of the time, I'm just going to refer to the empirical rule because it's nice, pretty numbers rather than getting something like 94.65% or whatever. I like 95%. It's pretty. So, so 3.2 in the hand and homework, please use the empirical rule. And and after that, if it tells you. All right, I think that's my last slide. It is. That's it. Any questions? Because that was the last slide. Questions for on the recording.
Okay, I just want to make sure I understand this.
Yes.
So on the the graph, is it always 34% in the middle and 13.5% on the sides, and then 2.35 and 0.15? Like, is it always that way so that
Yes.
it equals the okay?
Yes, that was a great question. Nobody has ever asked me that question before, but that is a fantastic question. Yeah, the diagram stays exactly the same. The only thing that changes is you can put numbers down here based on your data values. So whatever data they give you, that's when you can fill in the bottom part of the table. Like kind of like I did back here when I said randomly, I was like, okay, so I have that's ugly. Okay. So when I said that, okay, I'm doing 50 for my mean and then 2 for my standard deviation. So you just can label you'd label your drawing with whatever the data is you're using, and then it can help you to pull the percents off of the diagram. Okay. Click edit.
Oh, I
Oh.
just posted those so that they could
Oh, okay.
just in case they needed to calculate. That's what I wrote down. So
You are a rock star, Hannah. Thank you. All right. Anybody else? This great. I love good questions. Actually, I love even mediocre questions. So, and sometimes even off-topic questions, especially if it's about my cat. So, okay.
I have a question actually, and it was prompted by the co-requisite course.
Okay.
Are there any extra credit opportunities?
Very soon I'm not a big believer in extra credit. Okay, I'm going to preface this. I'm not a big believer in extra credit. I believe if you work hard and do the regular credit, you're going to be fine. But I will tell you that we're going to have there's going to be a practice test before the regular test, and the practice test will give you extra credit. So, I mean, that may be the only extra credit you get, but it's a little bit, it's a few points.
Okay, thank you.
I'm just not a big
What
believer.
is the co-requisite?
So there's a,
Uh,
oh, go ahead. You go ahead and explain it.
My understanding of it is it's a support class.
Mhm.
So it's an additional class you take. I don't know if everybody's required to take it, but I know some people are required to take it. Like I was required to take it because this is the first math class I've taken in like 4 years. And it's essentially a support class for this class. So it's another area where like I have Barner and she goes over some of the information that we learned during the week just to give us a different view into it essentially.
Yeah, so it's required for people who, so it used to be you had to take Math 65 before you could get into STAT 243. And so now they sometimes will allow people to skip some of the prerequisites if it would require them to have way too many terms of math to fit in. So in order to help them to people to not struggle as much, they have this co-requisite course that they require. It's optional for anybody. Anybody can take it, but certain students it's required for. And a lot of students that you've been out of school for a lot of years, they'll require it. But another person, it's a really great class. I love that it's offered. And if anybody has Fran Gunson, she was my stats teacher my first term at college, just letting y'all know. She's amazing. So I don't know if she's mentioned that. She sometimes does. So any other questions for on the recording? Okay, I'm going to unrecord.